Take a finite set of colors, such as white and black, and try to find a coloring of a grid that avoids a given set of forbidden patterns. Sometimes you will be able to do it, and sometimes you won't. This set of coloring, called subshifts of tiling, have a fundamental problem, which is called the domino problem. Given a finite set of forbidden patterns, does there exists such a coloring? It turns out that this problem is surprisingly undecidable. And the proof uses sophisticated sets of forbidden patterns to enforce some aperiodic, non-repetitive structures into which we can simulate universal computation. Thanks to these kinds of constructions, we can actually see that almost every interesting problem regarding tilings is undecidable as well.
Given the importance of the notion of aperiodicity in tilings, this talk focuses on a variant of the domino problem, the aperiodic domino problem, in which, instead of asking whether there exists a tiling respecting a given set of constraints, we ask whether there exists an aperiodic such tiling. In this question, a tiling is said to be periodic if there exists a vector such that the tiling and its shift are equal, and it is aperiodic if no such vector exists. This aperiodic variant of the domino problem can easily be proved undecidable as well, but we ask the following question: how much undecidable is it? Indeed, some undecidable problems can be proved harder than others, and in fact, a whole hierarchy of undecidability exists, and our aim is to study the position of the aperiodic domino problem in this hierarchy. Surprisingly, the difficulty of the aperiodic domino problem depends on the dimension of the coloring. There is a gap of difficulty between 2- and 3-dimensional colorings, and maybe between 3- and 4-dimensional ones as well, after which the problem attains its maximal complexity. As such, the aperiodic variant of the domino problem is an example of separation between 2, 3, and 4-dimensional tilings, for which they manifest different behaviors.